Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencaster. Zencaster is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencaster has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word, Breaking Math. Go to zencaster.com/pricing and use my code Breaking Math, and you'll get 30% off of your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your.
This is the story of the one. As a maintenance engineer, he hears things differently. To the untrained ear, everything on his shop floor might sound fine, but he can hear gears grinding or a belt slipping. So he steps in to fix the problem at hand before it gets out of hand. And he knows Granger's got the right product he needs to get the job done, which is music to his ears. Call, click Granger.com, or just stop by. Granger, for the ones who get it done.
Sabine Hossenfelder is a physicist who breaks down concepts in physics on her YouTube channel and has recently written a book, Existential Physics, which breaks down many obscure concepts in physics and discusses when unnecessary and confusing assumptions are often made. I'm Sophia, and this is Breaking Math. And with me, I have on Sabine. Sabine, nice to have you on today.
Hi, Sophia. Good to talk to you.
All right, so real quick, your YouTube channel, do you want to plug that really quickly before we move on to your book?
Yeah, sure. I have a YouTube channel which is called Science Without the Gobbledygook, and I talk about, broadly speaking, everything that I'm interested in science, but naturally, since I'm a physicist, I talk about physics a lot.
Cool. So what, I guess, drove you to write this book?
I think the major reason I was writing this book is that I was kind of a little bit depressed, really, after my first book, because really the first book is a community criticism. I'm pointing out what's going wrong in the foundations of physics. And a lot of the time when I come across headlines in the popular science media that address problems in my own research area, then the only thing I do is to say, no, you can't do this. No, this is wrong. No, this doesn't work. So I come across as being terribly destructive, cynical, and it's kind of not how I want to be. So I wanted to say, yes, physics sometimes tells you there are things which you can't do. You can't send information faster than the speed of light, for example. You can't make negative mass, no matter what the headlines say. But it also tells you that some things are possible. And I collected some of those examples in my book that I hope are a little bit surprising, ideas that have come out of physics that tell you something big about the universe, which you might not have expected.
Well, cool. So real quick on the whole front of one of the videos I first was became acquainted with your channel and stuff through was the delayed quantum eraser experiment, which debunks a seeming it debunks the fact that it seems like the past is erased. And I feel like that kind of do you want to talk about that and then dive into some of the concepts in your book?
Yeah, sure. So the quantum eraser experiment, this video came about because I was trying to understand this experiment. It was actually for a paper that I was working on, And I was looking up the literature on it, and I was also looking at the videos on YouTube in the hope of getting an insight. And it just didn't make sense to me. I was trying to do the maths, and I was writing down the equation. I was like, I think those equations don't say what the people on YouTube say they mean. And so this is why I ended up doing the video. So basically, what one does in the quantum eraser experiment is that one starts out with the double slit experiment. So in the double slit experiment, it has this peculiar property that if you send individual photons onto the double slit, then they can interfere with themselves. So you see an interference pattern which builds up from the individual photons on the screen. But if you try to measure which of the two slits the photon went through, then the interference pattern vanishes. And what one does in the quantum eraser experiment is that instead of using only one photon, one creates an entangled pair of photons, and on the one side, for the one particle in the entangled pair, one does the double slit experiment, and for the other one does a complicated other measurement. And then, to make a long story short, the idea is that you can somehow erase the information about which slit the photon went through after you've already measured it. So that seems pretty mind bending, because it seems like first you go and measure which slit the photon went through. So you should have destroyed the interference pattern. But then when you measure on one of the entangled photons of the pair, what happens? Then you can somehow recover this interference pattern. And so this is why people say you can kind of erase what you've already done.
So at the time that you had released the quantum eraser video,
Yes.
at the end you say that no one seems to be explaining this interpretation of the quantum eraser experiment, except for, I can't remember who you mentioned at the end of the video, but you said you could trust them on the quantum stuff.
Right. It was referring to a blog post from Sean Carroll, which I only found after I'd done the video, or after I'd written the script and everything, and someone pointed out, look, he's written about this here.
Gotcha. And so the way that you reinterpret it, it seems like you just kind of you take information that is unnecessary out, which is like your whole style, right?
Yes. So what I'm trying to say in the video is that to understand the quantum eraser, you don't have to do anything to the past. What you basically do when you tag those photons by the slit that they came through, you're creating groups of photons which you can later use to sample them into sets, each of which will give you an interference pattern. But if you combine them, you don't get an interference pattern, because the maxima and minima of the two sets, they are complements to each other. So if you combine them, then you get what you actually observe in the double slit experiment, if you know which slit the photon went through. So it all fits together.
Interesting. Yeah, that makes total sense to me, especially because I remember reading books on quantum physics and stuff from when I was a kid that didn't explain what measurement was, that it was a physical process. They kind of made it seem like, like there's this other world of observation and stuff like that, which of course to like anybody who'd studied physics for a few years would be like pretty clear, but to somebody who's unacquainted with physics, like like a kid studying just a book on physics, these confusing concepts can wedge their way into your mind in specific ways. So let's move on to your book. What I guess is your favorite chapter, or a chapter you want to talk about the most?
Well, of course, I like them all. It's like asking me which of your children is your favorite one. What am I supposed to answer to this? I think for me the most surprising one has been the one about the question whether the universe can think, because I totally expected the answer to be no. But it didn't quite work out the way I wanted it to.
Interesting. Do you want to go into some of that?
Yeah, so there's a standard argument that physicists make about why the universe can't think, and maybe I should step back a bit and explain why you may consider that the universe can think to begin with. It's because if you look at the distribution of galaxies from a really far distance in one of the galaxy surveys that have been made, then you'll find that the galaxies are distributed in filaments with clusters, and it kind of superficially looks a little bit like the connectome of the human brain, where you have neurons connected by axons and so on. So that brings up the question, like, if we have this structure in the human brain and it seems to be kind of similar to the universe, then maybe the universe can also think. Unfortunately, if you go only by the physics that we know and like already, the answer is no. And to make a long story short, the reason is that the universe is just too big. And we know that the speed of light is finite, and the universe is some tenths of billions of light years from one side to the other. So it takes a long time to send a signal from one side to the other. So even if the universe was thinking, it can't think very much. So
Yes,
this is
and this is kind of related to the concept of speed in neurons, like the axons, correct? What is it? Cerebral neurons have a speed of something like 300, like 100 meters per second. The skull is something like 20 centimeters across. So what is that? A frequency of something like 250 hertz. That like a neuron could go to the back and forth of, right, of the mind. So what you're saying is, like, for the universe, for the universe to be able to coordinate all its thoughts with one another, it would need a very extended
yes,
time
that's
span.
right, and we're talking more than trillions of years, but the universe has only been around for about 14 billion years, and it has an additional problem, which is that it's expanding, and the expansion is actually speeding up, which makes it more difficult to communicate from one side to the other, because the galaxies are moving apart from each other. So from here on, it's just going downhills. So so the problem is basically that the speed of light is finite, and even though it's very large compared to the speed by which our brain sends around signals, it doesn't make up for the huge size of the universe. Okay, so this is for what standard physics is concerned, so to speak. Um, but I've been working for a long time on quantum gravity, so this is the missing combination between quantum mechanics and gravity, which we're still working on. And one of the things that has come out of this line of research is that our notion of locality might not quite be correct. So, what do I mean by locality? What we mean by locality in physics is that if you want to interact with something, loosely speaking, it has to be nearby. So, if you want to send a parcel, it has to go some way from the sender to the receiver. It can't just disappear into a portal and suddenly reappear somewhere else. That's something which we don't observe. And we're pretty sure it doesn't exist, at least at the sizes that we have been able to look at. And that goes down to elementary particles. In the most extreme case, it's being tested at the Large Hadron Collider, and it's about 10 to the minus 20 meters or something is the typical distance which they test there. But if you go to even shorter distances, something like 10 to the minus 5 centimeters, this is where you reach the Planck scale, then it's far less clear what is with this notion of locality. And there are some people who have suggested that actually, if you go down to this very short distance scales, then there should be basically teeny tiny wormholes that would be connecting the universe one end to the other everywhere. and there would be a lot of those connections. And now let me be clear, those are so small that we can't go through them, and even the elementary particles can't go through them, but they would still connect the geometry of the universe with itself. And
Almost
so
like it seems almost like knitting the tangent bundles and stuff like that in just the geometry of the space time, kind of like
yeah,
almost like knitting
it's
together
not it's not the
fibers.
tangent bundle. I mean, you have to, if you want it to be differentiable, you have to make sure that the tangent bundle supports the differentiable geometry. But most of the time, people treat those, it's called a non-local link, as something which just doesn't fit to the geometry. If you want to make it more sophisticated, then I guess you would have to change the topology of the space-time.
Gotcha,
But
gotcha.
yeah, but normally the way that people think about it is that the entire universe is just a big network that, on those large scales that we observe, approximates a manifold to good accuracy. And this is why we can, in Einstein's theory, use four-dimensional Riemannian differentiable manifold. But really, if you look at short distance scales, then you have all those non-geometric, non-local connections. And so this seeming need that you need to be close to something to interact with it might just disappear if you go to very, very short distance scales. And it's something that the universe might be able to do. And this is something which we just can't rule out based on everything we know right now, because we don't actually know what this theory of quantum gravity looks like. There are other reasons that people have put forward why this notion of locality that we currently use might not be entirely correct. The black hole information loss problem is one of them. Then there's quantum mechanics, the measurement problem. You already alluded to this. So there are a number of reasons why the locality that we observe seems a little bit suspicious. And this is why I think it's possible that down there at those very short distance scales, the universe is actually much more connected than it appears to us. And now, does this mean that the universe can think? Well, not necessarily, but it would probably mean that it has enough connections to do at least as much thinking as the human brain. And I'm still trying to to figure out what to make of this.
Interesting. Yeah, that is fascinating. So you talk about these. You just talked about these wormholes being so small that even elementary particles couldn't go through. So would this mean that if this neural structure, did exist and these were the connections between them, that whatever thoughts this neural structure had would be inaccessible to us, basically?
Well, we actually do measure the properties of space-time. For example, when we measure gravitational waves. So gravitational waves are not themselves particles made of matter, but it's also not radiation. Instead, what we measure is we measure the influence of those space-time perturbations on the normal matter. So, in principle, if you want to stretch your mind, it's possible in principle that there be some configurations of those non-local links that might become observable. If they cluster enough, basically, you could see an influence of this on the normal matter that we have. But to be fair, we don't really know a terrible lot about them.
Interesting. What kind of influence? Do you want to go into what kind of influence that you're talking about specifically?
Well, it's all speculation. So let me be clear. There's absolutely no evidence that this is correct. But I mean, there are some people who have argued that such non-local connections could actually have an effect quite similar to dark matter, in the sense that those non-local links would basically multiply and distribute the gravitational influence of a mass. So if you think about some kind of matter clump, like a star or something that creates a gravitational field. And you have those non-local connections that start close by the thing, but they connect it to a different place that might be very, very far away from the star. Then at this faraway place, you would now feel the stronger gravitational field from close by the star. So the effect of the distribution of those non-local links could be that the gravitational attraction of some kind of source doesn't fall off as quickly as general relativity would predict. And that's pretty much exactly what we see when we look at galaxies or galaxy clusters, which is normally attributed to dark matter. So now this sounds kind of good at first sight, so to speak, but if you think about it a little deeper, then you're really just replacing the distribution of dark matter with the distribution of those non-local links, and in the end you don't really gain anything. It doesn't really help you with anything, and it brings in some new problems. So I'm not terribly excited about it, but it's certainly something that people have put forward. I myself wrote a paper about this, like, I don't know, 10 years ago, so I can hardly remember what's in the paper. But I was trying to address the possibility that energy can diffuse through those non-local links. And that would basically have the effect that particles would lose energy as they travel. So you see some kind of slowing down of highly energetic particles, and this is something which you can look for. It's not been seen, but those are some possible effects.
Interesting. Yeah, it's all very. It seems all very strange when you get to that kind of. I mean, it's almost like a cliche at this point to say that, like, it's strange when large and small scales interact. But it kind of just reminds me also of the stress energy tensor. The stress energy tensor being a combination of, for our audience, the energy density at a point, or shear force, or pressure in any specific plane. And it's a 4x4 tensor, and it's used in the Einstein general theory of gravitation. And it always struck me that, at the smallest scales, you have these atoms bouncing off of one another, which really create the basis for pressure. But yeah, just to add on and say that I think it's that all sounds very fascinating. So now let's move on from. So that was perhaps the most surprising chapter. And is it unless it's the same answer? Do you have a chapter that you did that was perhaps the most technically difficult to get through?
Definitely the first one, because the first chapter is the one about the question whether the past still exists. And this is a standard argument which you find in pretty much all textbooks on special relativity. But it's really hard to explain without writing down equations. And I've tried to do it mostly in words so that you'd still be able to follow it in the audio version, but I heavily rely on space-time diagrams, and I hope it kind of came across, but this was definitely challenging. I can maybe add something to the stress energy tensor since you mentioned this. This is actually the way that it works with those non-local sources. You change the influence of the stress energy tensor. You spread it out basically. And actually, it's quite interesting that you brought up the question, like, what's with the elementary particles? Normally, the stress energy tensor that we use in general relativity is considered to be a kind of an average. It's not really something about the elementary particles. And now, as you certainly know, Einstein's field equations are nonlinear. So taking an average of the source isn't quite as trivial as it sounds. So strictly speaking, we're not even sure that we're solving the right equations when we're doing cosmology.
That's kind of fascinating in its own right. I mean, yeah, cosmology seems kind of fascinating too. From the I guess here's a question that perhaps you'd be able to answer. Just speaking of this sort of cosmology. So I've looked at diagrams of the past. They have these different epochs that have different rates of expansion, right? Mm-hmm. So I was. I've always wondered what let me see if I can phrase this. Is it possible that it's smooth expansion that's being distorted at points in some strange way?
You mean when you cross over from one epoch to another?
Yes, yeah. When you cross over from one epoch to another, like
Okay. Well,
because
so I guess one thing I should say is that in general relativity, you are free to choose your time coordinate. Technically, there are infinitely many choices of time coordinates that you could make. None of them is really any better or worse than the other. Often, the time coordinate that physicists choose is what's called the co-moving time. That means it moves with the matter, so it's like the proper time of the matter. But of course, this is if you're doing cosmology, you're talking about a homogeneous distribution of matter in the entire universe, which is, of course, not strictly speaking correct. And if you do this, then you have those rather artificial looking sudden transitions from one epoch to another when, matter takes over radiation or inflation stops or something like this. But if you were to look at this more realistically with inhomogeneities, then those transitions would smooth out.
interesting. Yeah, I always find that fascinating. I feel like when you're dealing with speed of light kind of stuff, and it doubly so cosmology, you have that kind of like effect where like almost like the subject matter is slipping away from you as you study it. I get the same feelings when I've studied the fluid dynamics equations a few times. So I guess I want to ask you too. Is there anything about your specific background that led you to? You told a little bit about the factors that led you to wrote your previous book and how the experience from that led you to write this book. But is there anything from your career specifically, either be it an event or a general progression, that led you to be fascinated in, I guess, these kind of questions of I guess would you call that scientific ontology?
Yeah, I guess it's because so I originally didn't study physics. I studied mathematics, and I did this for like 3, 4 years or something. But I really love mathematics. The problem was I loved all of it. Like it was all great, but then you come to a point where you have to make a decision, like which mathematics do you focus on? And I decided I would focus on that part of mathematics which was good to describe nature, and that naturally led me into physics. But I've always been fascinated by the question: how much of nature can we describe by mathematics? How much can it do for us? And you find this in several places in my new book. So I partly wrote this book to remind myself of why I was interested in that question and why I find it so fascinating that physics can tell us all those things, which we, in a very concrete way, pretty much deduce from mathematics.
Yeah, we talk a little bit in our podcast, actually quite frequently in our podcast, and specifically we did episode 4 of our podcast about this interesting relationship between the physical world and the mathematical, I guess, realm. You have physical uses of math that aren't useful for much long after, but then sometimes you have discoveries in physics, which end up in mathematics, or like lead to discoveries in mathematics. Even you see this a ton with biology and computing, to just give like, I guess, a middle ground type of example. So it is fascinating too, because I think I read somewhere about the incomputability of the three body system given a finite amount of space or something like that. I can't remember exactly what it was. Physics can be described by mathematics. So is there anything that leads you to believe that there are some physics that can't be described by mathematics? Because it seems to me that mathematics would be just a logical set of observations that you apply to other observations, I guess. And it seems like if those observations are consistent with any set of rules, then there would be some set of mathematics to explain them.
So yes, this is a very common argument to make, that if there's any kind of pattern that we observe, then there has to be mathematics to describe it. It's almost tautologically true, like the thing that we call a pattern, that is already mathematics. I have absolutely no reason to think that there's any observation in in nature in general, not just in physics in particular, that cannot be described by mathematics. But I've entertained the thought, if it's possible to do science without mathematics, and maybe somewhat disturbingly for you, I come to the conclusion you can conceivably do it. That's because if you think about it, what we do in many cases is that we use mathematics as kind of a middleman. We extract a pattern from one system, from our observations, and then we use another system. For example, it could be a computer, but it could also be a direct simulation. We use this other system to help us make a prediction for the first system. And in principle, you can take out mathematics as the middleman. You can just try to find two systems that kind of mimic each other, where one is simpler and helps you to make a prediction for the more complicated one. So I think you can do this. To some extent, you could say we are already doing this in a research area that's called quantum simulation. So quantum simulations, you can use fairly complicated condensed matter systems to try and mimic the behavior of elementary particles. Every once in a while you see this in the headlines, and headline writers frequently get it wrong. They'll be talking about the discovery of some new kind of particle, but it's actually a particular excitation in some kind of material. So it's called a quasi-particle, not a fundamental particle, but on some level, mathematically, they behave the same way. So it's quite exciting, and you could think that maybe one day you could just use some custom design condensed matter system to actually simulate what's going on in an elementary particle collision, and you don't actually need the mathematics in between.
That reminds me of a short story that I read by I want to say like Isaac Asimov or Arthur C. Clarke, where there's a society far in the future that where this person decides to write down a problem. It's like 35 times 73 and solves it on a chalkboard, and everyone is amazed because everybody's used to carrying these calculators around them. And somebody asks, wait, is that true every time? And then at the end, they end up trying to use humans as guidance computers for missiles. It's some kind of political point that I forget exactly what it is. It's a very old story, but yeah, that is a fascinating idea. Especially, it reminds me of a little bit of an experiment that I read from a few years ago, where liquid helium was being used to study black holes. Specifically, like sound waves or something were being sent into swirls, eddies, something like that. Yeah, so that is fascinating. And it even has the property of mathematics, that mathematics is a simplification of the real world in many extents. I mean, it's just that whole old argument of the Platonic ideal versus whatever you want to call that.
Yeah, the superfluid helium is actually an example of a quantum simulation. It's more specifically known as analog gravity. So analog as in it's an analogy, not analog as opposed to digital.
I mean, it couldn't even make the argument that no mathematics has ever been used in physics if you wanted to get very strange in it. So, for example, if we simulate the system, like let's say we want to know what happens to a star under certain conditions, I don't know, some kind of physical experiment, we do it in a quantum simulation that simulates it with a high degree of precision. We're still going to have some opinions about this information. There had to be a reason why we came up with the information in the first place. This is just the way in which we use physics, is just to explain it, and that perhaps mathematics is our convoluted current way of explaining it.
Yeah, I think that's one way to look at it. Though I guess it's arguably true. Like, for example, if you look at something that we would do in numerical general relativity, we put the whole thing on a computer. And the computer solves some kind of differential equation, basically. But you could also look at the computer itself as a system that's just, in some sense, being mapped to the other system. I would still say that it's also mapped to some mathematical structure. So the mathematics is there somehow, but the question is, do you actually need it?
And then you could get even like more like you get further pedantic with it, I suppose. And or then argue that the physicist or that the history of physics itself is the material that that the mathematics is made of, so that there's not actually a separation between the two in such a sense. But I feel like at that level, getting too almost fine grained.
Yeah. I guess most physicists would kind of say it's the other way around. It's not that the math is made of the physics, but it's that the physics is made of the math, if that makes sense. But yeah, I mean, it gets very philosophical at this point, I suppose. I'm kind of out of my depth there, I'm afraid.
I guess we'll move on to is do copies of us exist?
Yeah, sure. So the question whether copies of us exist comes up in this idea of the multiverse, which has been kind of popular in the foundations of physics in the past 1-2 decades. There are several different types of multiverses. Brian Greene has written a book about it in which he lists 9, but I think I'll not go through the whole list. I'll just tell you the ones that you're most likely to have heard of. I guess the best known one is the many worlds interpretation of quantum mechanics. So normally, the way that quantum mechanics is taught to students, the story has it that in quantum mechanics we predict probabilities for measurement outcomes. And we predict those by the use of what's called a wave function. So the wave function contains all those possibilities. For example, if you're measuring one particle, just to keep things simple, and the particle either pops up on the left side of the screen or the right side of the screen, then the wave function might tell you, well, it's 50% left, 50% right. But then the moment you measure the particle, the probability jumps to 100-0. And in the standard interpretation, you would then go and update the wave function. So it's called the update of the wave function, sometimes the reduction of the wave function, or the collapse of the wave function. It's all the same thing. So now in the many worlds interpretation, the story has it that no, you don't update the wave function. Both of these measurement outcomes actually happen, but each of them happens in a separate universe. So in this case, you've split the universe into 2. And this basically happens all the time and everywhere, depending on how many possible outcomes an experiment has. You get less of those universes. That makes for a lot of universes very, very quickly. So that's the many worlds interpretation. There's also a specific theory for the beginning of our universe, which is called eternal inflation. In eternal inflation, our universe is created from a fluctuation in a quantum field. But the thing is that there isn't only one of those fluctuations that can make a universe. There are infinitely many, so there are constantly universes being created. So there are lots of other universes. And then to add a final one, it's the string theory landscape. So in this string theory landscape, there are different combinations of the fundamental constants of nature. So for each of them, you can have a different universe. And so what happens in those universes, like take for example the many worlds. So each time a quantum measurement happens, or you make a quantum measurement, so quantum measurements don't actually need an apparatus. I should have said this. Just if the particle hits a wall, this will also collapse the wave function or split the universe, depending on which way you look at it. So now there are 2 versions of you. The one in which the particle hit the left side of the screen, and another one in which it hit the right side of the screen. And in your brain, there are constantly quantum processes going on, and those could have different outcomes. And so every time you kind of make a decision in which a quantum process was involved, which we don't really know how much they are involved, but it's just for the sake of the argument, assume it is involved, then there are now several different versions of you. And each of them has made a different decision and continues to live their life in a different way. And similarly, in eternal inflation, where you have all those different big bangs, those universes, some of those elementary particles are a tiny little bit different. So you're pretty much the same person that you're in this universe, except that, I don't know, there's a tiny little difference in your genetic code, and that'll lead you to choose a different profession. Maybe you're not making a podcast. I don't know, maybe you're into writing books or something like this. The problem with all those other universes that you have in the different versions of multiverses is that we can't observe them. And it's not just that it's difficult and we haven't yet been able to do it, it's impossible even in principle. Like, for example, in the many worlds interpretation, the whole point about splitting the universe is that you don't see the other outcome of the experiment. So you don't measure it. So why do physicists believe that those other universes actually exist? Well, it's because they show up in their mathematics. So basically they say, well, I have this big piece of mathematics, and some of what I see in my mathematics corresponds to what we actually do observe. Therefore, I deduce everything I see in my mathematics also has to exist. And it's this last step, which I think is not a particularly good conclusion. But I mean, if you want to, you can believe that those other universes exist. It's not that there are any observations that speak against their existence either. So I would say this is, as my friend Tim Palmer put it, an ascientific belief. If you want to, you can believe in those other universes with copies of you, but you shouldn't think that science actually delivers evidence for it.
Interesting. So, what led you, by the way, to start studying mathematics? You said you started with mathematics. Did you always have an interest in mathematics?
Well, yeah, kind of. I was always good at maths. I think that's where it came from. My mother, I should say, she's now retired, but she was a high school teacher for maths and biology, I should probably add. So the physics didn't come from there.
Oh, interesting. My mother was also both a math teacher and a biology teacher. All right, I guess a final question. Your epilogue, I love the title. What's the purpose of anything anyway? I know the epilogue, so it kind of summarizes the book, so it's probably not summarize the book, but kind of is a closer to the book. But did you want to talk at all about that?
Well, yeah. So in the epilogue, I try to put forward my own thoughts about what's the meaning of life, what's the purpose of anything anyway. And one of the points that I'm trying to get across is that I think it's not really a question that science can possibly answer. Meaning or purpose of our lives is something that everyone has to find for themselves. And if you ask me what I think the meaning of my life is, what's the purpose, I would put this into science communication, which makes a lot of sense to me. I explain other people what I found in the foundations of physics, and that gives meaning to my life.
I think it's a great thing, honestly, that you as a physicist are putting that view forward. Existential Physics, A Scientist's Guide to Life's Biggest Questions, is a book that's all about, what it says on the title and what we talked about today. I recommend that y'all buy it. It's a very fun book. It's big enough to have you spend quite a bit of time on it, but not where it's either intimidating or so. Sabine, any final remarks?
No, that were really, really good questions. It's great to talk to you.
Awesome. So yeah, check out her book, check out her channel, Science Without the Gobbledygook, and keep listening to Breaking Math. We never know how to actually finish the show on this program. We just kind of let it end.
For the ones who know safety isn't a catchphrase, it's a culture. And the ones who help make sure everyone makes it home safe. For the safety-minded who watch everyone's backs, Grainger offers supplies and solutions for every industry, as well as safety assessments and training to keep your facilities safe and your people safer. Call, click Grainger.com, or just stop by. Grainger, for the ones who get it done.